All right, let's create some mathematical models based on what we know about exponential functions. Einsteinium is a radioactive chemical, and in this story, I don't know if this is accurate, but it's probably true that it has a decay rate of 3% per day. So the molecules are giving off electrons and it decomposes with time. And if we start with 10 micrograms, how much Einsteinium will we have after a week? Well, let's set up some variables here. So I just wrote down a couple quick facts to get us going. We're going to let t equal the number of days, because I see the decay rate is talking about it in terms of days. And the initial value is 10. Okay, so that's our y-intercept point, which is also a. So our equation is half created here. E is going to equal ab to the t. Well, we just figured out that that is 10b to the t power. So all we need to do is figure out b. Now we don't have any other clues except one. We haven't used anything about this 3%. But the 3% is a decay rate. R equals negative 3%. Because it's decay, we're losing. And so when you divide by 100 as a decimal, R is going to equal negative 0.03. So be careful to divide by 100. It's going to change the decimal 2 positions. And we can use that because we have a formula for B. It equals 1 plus the percent growth rate. Well, it's not a growth this time. It's a decay, so we're going to subtract 0.03. And so B equals 0.97. We're done with the equation. We've got the whole thing here. E equals 10 times 0.97 to the t power. There is the equation. Now notice the B number is smaller than 1. When it's smaller than 1, you are going to get decay. And that's what the problem says. Einsteinium is a radioactive chemical, so over time it loses its mass. And ask your physics teacher about the rest of that. But we did have a question to expand on this week, 1 week, which is t equals 7. So all we have to do is plug that in and do the math. So I'm going to kind of speed that part up and just show you the outcome. So once we plug it in, it's just a matter of doing some calculator work, and we're going to get about 8 micrograms. So after a week, the Einsteinium has decayed down to 8 micrograms. Let's take a look at this other example here. India's population is growing at a rate of 1.2%. In 2016, they had about 1.324 billion people. Write a function to model India's population in billions of people. And then we have a follow-up question. How big will India's population be in 2025? So I'm going to start by writing down our variables. So if we let t equal the number of years after 2016, and then p is the population in billions, well, in 2016, that's when we're starting our analysis. So our starting t is 0. That means we have this initial point. So this is our a number. So our equation is half built already just because of the convenience of how we set up the t by using these two words here. Okay, so let's get the equation started. Okay, so I just took the standard basic exponential function here and I plugged in my a value. So I've got a good start on the equation if I can just find b. But b, especially when we have percent growth or percent decay, b has this formula 1 plus r. And in this case, R is a growth rate of 1.2%. Now be careful here. When you change percent into its decimal value, divide by 100, and it's going to move the decimal twice. Sometimes people lose that 0 in front of the one-digit percents. So that means we've got B equals 1 plus 0.012. So B is 1.012. That is the rest of my equation. So P equals 1.324 times B, 1.012 raised to the t power. That is the equation that models India's growth here. Now we had a follow-up question in 2025. Now remember, we're not plugging in 2025. We're talking about t. T equals years after 2016. So if we subtract, we're going to find out that that's 9 years after. So all we have to do now is just some calculator work and plug this in. Okay, so once we plug this in, we're going to get the population is approximately 1.474 billion people. I read somewhere that this population of India is going to exceed the population of China. So I don't know if that's going to play out like that, but there's a model that we have that we can analyze this data. Okay, so we've got a couple examples under our belt here. You'll see more of these in the homework and in Newton, so practice this.